So we go to the next section, okay, 2.2.6. Okay, we would have a little bit about energy balance in a closed and open system. So we will first state the first law of thermodynamics, and then we will talk about the energy balance. In this section, we will discuss how to do energy analysis for closed and open system, where more details will be discussed in Chapter 4 and Chapter 5 respectively. Here we just give a general idea to you on how to apply the conservation of energy principle for a general system. Well, here we first state the first law of thermodynamics, okay? In a mathematical form, that will be this one, delta E equal to Q minus W, where the Q is the net energy heat input to the system, and W is the net work output by the system, okay? Well, described in words, it is the total energy increase of a closed system that's equal to the net heat transfer into the system minus the net work the system does on the outside, okay? It can be extended to open systems if we also consider mass transfer across the system. Okay? Well, this law not only establishes the existence and the definition of total energy E, but also states the conservation of energy principle. Okay? Well, here, if we put Q equal to 0, then we will get the following second statement. Okay, that is for all adiabatic processes between two specified states of a closed system, then the net work done is the same regardless of the nature of the closed system and how the process is carried out, okay? Because internal energy is a point function, okay? So here we also assume that the system does not move and it also have no potential energy change, so that we will have this kind of expression, that is the internal energy will be equal to the work done. Here it's interesting to see that a path function is equated to a point function because the nature is totally different, but they can be equated, okay? Just like what we see in a work energy field, okay? And because of this conservation of energy principle, we have derived the energy balance equation, that is E in minus E out equal to delta E of the system, okay? That is the change in energy of system is given by subtracting the energy at the final state by that at the initial state. Okay, that is a final minus initial. Okay, for a simple compressible system, the energy change is only due to the change in internal energy, kinetic energy, as well as the potential energy. Okay, because we just have these three kinds of energy inside a simple compressible system, so that we can write this change in energy of system to be in this expression. Okay. For a stationary system, which is common to be seen in practice, okay, there will be no change in kinetic and potential energy, so that this term vanishes and this term vanishes, so that it becomes delta E equal to delta U. Okay, so here we have an intuitive example. Suppose we have shaft work, okay, that is some work done brought into the system by rotating shaft, that will be equal to 6 kilojoule. And there is Q in equal to 15 kilojoule and Q out equal to 3 kilojoule. So what's the delta E? Okay, well, intuitively, there should be some energy into the system. So this should be positive, this should be positive, and we need to minus this Q out. So that we have 15 minus 3, that will be the net heat input, and 6 will be the net work input into the system. So it will be equal to 18 kilojoule. Okay. So this can be stated in a very intuitive sense, okay? There are only three types of mechanisms of energy transfer, okay? That is by heat transfer, work transfer, as well as mass transfer, okay? Mass is actually energy, okay? Given by the famous formula E equal to mc squared. So when there is mass flow across a boundary, there will be energy transfer, okay? While heat flow into a system, work done on the system, as well as the mass flow to the system will increase the energy content, while the heat flow from the system, work done by the system, as well as the mass flow out of the system will decrease the energy content. Okay, you can develop this by using very intuitive idea. Okay, this complies with our intuition. Okay, as a result, we can also restate the energy balance in this kind of expression. Okay, that is E in minus E out equal to Q in minus Q out plus W in minus W out plus E mass in minus E mass out. Okay, that's equal to the delta E of system. Okay, so we just group the terms into different groups according to the nature of energy transfer. Okay, for closed system, only energy crosses the boundaries, so only heat and work is involved in the energy interactions. But for open system, we also need to include the energy transfer by mass. Okay, so the below figure will show the example of open and closed system. Okay, so here, for the previous example, so I have also showed this one, it is an example of closed system because you can see that no mass can actually cross the boundary because it's a closed container. Okay, in this case, it is a closed container. Okay, but for open system, because both energy and mass can cross the boundary, so that we will have also mass in and mass out in addition to the work done or the work interaction and the heat interaction. Okay? Okay, here we also have a rate form and also the energy balance equation in a unit mass basis. Okay, here will be the rate form. Okay, E dot A minus E dot out will be equal to dE dt. Okay, here I have mentioned that I should not use a dm dt in the very beginning when I'm talking about the mass flow rate. Okay, I just want to illustrate that the time rate of change will be something equivalent to ddt, but actually I can't use this kind of symbol because this kind of ddt, we are just talking about the change in the property. Okay, change of property. But for mass flow rate, it's a kind of mass transfer, but not some property possessed by the system. Okay, so here I would use the over dot here. Okay, and we also have energy balance per unit mass. Okay, that would be E in minus E out equal to delta E of system. Okay, well, we also have a differential form of the energy balance equation that would be a delta E in minus delta E out equal to dE of system, or in a per unit mass basis. Okay, so note that this delta and this d are different because this delta we are talking about part functions. Okay, that is the energy transfer terms. But for this d, we are talking about point functions because E of system is a kind of property possessed by a system. Okay, so you need to be aware about that. Okay, for closed system undergoing cyclic processes, the initial state and final state are the same, so there will be no change in the energy content of the system, so that delta E will become 0. Therefore, we will have Q equal to W. Okay, Q is W. And if we write it using our sign conventions, we will have a W net out equal to Q net in. Okay, so net heat input equal to net work output. Okay, or in the raised form. Okay, by adding a dot over the symbol for cycle. Okay, these two are for cycle only. Okay, so if you have a certain amount of heat inputting in the system, then you should have the same amount of work done flowing out of the system. That means the work done by the system. Okay, so that there will be no change in the energy inside a system. Okay, so below will be some example to illustrate how to apply the energy balance in real life situation, and you will see it in the next video.